In this problem, we're given a radical function, its graph, and a table of values. We're asked to state the domain of the given function in interval notation. Let me start by saying that using a table of values or a graph to find the domain of a function is not the most accurate approach. As a guide, they're very helpful, but the representation of the function that's best in finding the exact domain of a function is its equation. Think of the domain of a function as the set of all x values or possible inputs for which you will get a defined output. So for example, because this equation involves a square root, let's discuss the meaning behind the problem before I show you how to get to the answer. Getting the answer is very easy, but if you don't understand why the answer makes sense, you will not be able to do problems similar to this one. You'll only be able to do this exact problem. Let's define what it means for something to be in the domain as opposed to out of the domain of a square root function. For example, given the equation for my function f, let's plug in x equals 0. At x equals 0, we would have that f of 0 is equal to the square root of 0 plus 2, which simplifies to be the square root of 2. This is an example of an x value that's in the domain of the function because my output, square root of 2, can be calculated in what's called the real number system. The square root of 2, if you were to type it in your calculator, you would get about 1.4142 because the output at x equals 0 comes out to be the square root of 2. This is why you see 1.4142 in the table of values. That's a rounded version of the square root of 2. Likewise, on the graph, if you look at the point on the graph whose x value is 0, you see that the y-coordinate is between 1 and 2. About 1.5, but more specifically about 1.4. Let me give you an example of an x value that's not in the domain. This would be easy to see on the table. Here are some examples of x values for which the function is undefined. They show up this way in the table. They also show up on the graph in the following way. If I was to ask you what is the output when x is negative 5, looking over at x equals negative 5, you see that there's no point corresponding to that x value. The fact that there is no point means the function is undefined. The problem with a graph, however, is that no graph is ever complete. The graph could actually exist outside the window for which the graph was drawn. So again, the graph is just a guide. The real way to find the domain is to actually use the equation. So back to the equation, let's look at an input value for which the function would be undefined. Let's pick x equals negative 6. At x equals negative 6, the table does not tell me what's happening with the function at x equals negative 6. Also, the graph shown here wasn't even drawn at x equals negative 6. However, I can show you that x equals negative 6 is not in the domain of the function by using the equation. So replacing x with negative 6, we get that f of negative 6 simplifies down to be the square root of negative 4. Whenever you take the square root of a negative number, the result is a number that's not in the real number system. It is in what's called the complex number system. That's for another video. When we ask to find the domain of f, the intent is to find input values that give real number outputs, not complex number outputs. Remember what the square root means. It means there's some number, we could put it in the blank here. When you multiply it by itself, you get negative 4. There is no real number for which this works. You may guess 2 times 2, but that would give you positive 4, so that doesn't work. You may be thinking negative 2 would work, but remember that a negative times a negative is a positive, so that wouldn't give you negative 4 as well. There's no real number that when you multiply by itself, you'll get a negative number, so this simply will not work. In fact, any input that makes the number under the radical negative would be excluded from the domain. And by the way, the number under the radical is called the radicand. So all this was nice to show you specifically what it means for an input to be in the domain or what it means for an input to be not in the domain, but a more straightforward approach would be as follows. Copy the radicand down, the x plus 2, and simply state what we need to happen. We need the radicand to come out to be a positive number, that means greater than 0, or it actually can be 0, because if the radicand came out to be 0, you'd have the square root of 0, which in math is defined to be 0. In fact, in our problem, that happens at x equals negative 2. If you replaced x with negative 2, your radicand would be negative 2 plus 2, or 0, and the square root of 0 is defined to be this right here, an output of 0. So this right here happens at the equality, when x plus 2 comes out to be 0. Also on the graph, it happens to be the endpoint of our graph. When x is negative 2, the output is 0, and that's the point here, negative 2 comma 0. So all I have to do is set the radicand greater than or equal to 0. I can solve in this case by simply subtracting the 2 on both sides. When you add or subtract with an inequality, you need not change the sign on the inequality. So my answer is x is bigger than or equal to negative 2. And again, the table on the graph will help as a check. Notice that I have answers when x is either negative 2 or bigger than negative 2 on the table. And notice on the graph that the graph exists everywhere to the right of x equals negative 2. That means if you're to the left of x equals negative 2, the function's undefined. But if you're at negative 2, and this is what that line means, when x is negative 2 or bigger than negative 2, meaning to the right of this red line I drew, then your function actually is defined. You're actually getting points. For every x value, you see some corresponding output. Now, one thing to notice is that I've expressed my answer in inequality notation, but the directions said to state it in interval notation. So assuming you know interval notation, we need to express numbers that can be equal to negative 2, so that would require a bracket to indicate that the negative 2 is included in the domain. That would be the smallest number in my domain. Because we want all numbers greater than negative 2, and that goes on forever, we use an infinity symbol. And then since you can't actually reach infinity, in fact it's not a real number, we put a parenthesis here. If this is a computer-generated question, it's likely that you can enter infinity using 2 lowercase o's on the keyboard. Now if we give you a more complicated function, hopefully you realize it's the square root that's causing this issue for some x values to give valid outputs and other x values that produce no valid output of the function. So if we were to change the equation, such as negative 3 subtract 5 times the square root of the quantity x plus 2 all divided by 1,000, hopefully you see that the domain would still be exactly the same. And the reason is it's only the radical that's going to change the domain. As long as this radical is defined as a real number, you can take any real number and multiply by 5. You can take any real number and subtract it from negative 3. You can take any real number and divide by 1,000. So adding all these features to the equation makes no difference relative to the domain. With this structure, it's only the radical that creates the issue, and the issue is when the radicand comes out to be a negative number. So our strategy was to simply make sure that that radicand never comes out to be negative. We did this by saying, please make sure that my radicand, which is x2 in my case, comes out to be positive, bigger than 0, or it could be 0.